Hey guys, welcome to the Section 6 discussion video on Bayes nets. So today we're going to be talking about a couple of things because this discussion actually covered the last 2 weeks of material. So here we're going to be covering independence in Bayes nets, and that's going to be mainly D-separation. We're going to be talking about inference, so the variable enumeration algorithm and the variable elimination algorithm. And then we're going to be talking about sampling, which we covered these 4 sampling algorithms for Bayes nets in class. So we're going to be covering all of those. All right, let's get started. So we'll start by talking about D-separation. And basically, D-separation is very simple. For any Bayes net, you can kind of think about, instead of individual nodes, you can think about these triples. So we have one triple, which is the causal chain, which is just one pointing to the next, pointing to the next. We have a common cause, where you have the middle node that's pointing to 2 children. And then you have the common effect, where you have 2 outer nodes and they influence the middle node. Now, the point of these triples is so we can kind of use them to read off independencies in our Bayes net. And to do that, we'll have this notion of active triples and inactive triples. So when you see the gray shaded in middle node here, what it means is this middle node has been observed. Or in other words, it's one of the condition variables. It's one of the evidence. So basically, what this tells us is if we have a causal chain where the middle node is not observed, then this is an active triple. This chain is active. If the middle one is observed, then this is now an inactive triple, and so on and so forth, right? How do we use these to tell independence between 2 variables? Basically, 2 variables are independent or conditionally independent if there are no active paths between the 2 variables. Okay, so what a path consists of is kind of all triples between the 2 variables, and a path is active if all triples on that path are active. So if there's a single triple on that path that's inactive, then that means the entire path is inactive. And if there are no active paths between 2 variables, then that means that those 2 variables are independent. So another thing is we can guarantee that 2 variables are independent, but we can't guarantee that they're dependent. Okay, let's look at some examples of D-separation. Alright, so here we have a standard Bayes net with 5 variables, A, B, C, D, E. And we have a couple of queries that we're going to go through. So the first one is A independent of D given C. So let's go ahead and shade in C because it's observed. And now what we want to do is we want to look at all of the paths between A and D. So the 2 paths are going to be ABD and ACD. And now we want to see if we can find an active path. Okay, so if we find one active path, it means that A is not guaranteed to be independent of D given C. If we don't find any active paths, what it means that they are guaranteed to be independent. Okay, so let's just look at the paths. Well, we look at this triple ABD, and we see immediately that this triple is active. Okay, so this is an active path right here. ABD is active. And at this point, we already know that these 2 variables aren't guaranteed to be independent, but let's just look at the other one, right? Let's just look at the other path just for the sake of it. So ACD. This triple will be inactive because this is a causal chain where the middle one's observed, which is an inactive triple. So here, of the 2 paths between A and D, we have one inactive one and one active one. And because there's an active one, what that tells us is that A is not guaranteed to be independent of D. And so we'll say it's not guaranteed. Okay, let's look at a different example. So now we have, is A independent of D given both B and C? So let's go ahead and shade those in. So we saw before that the causal chain with the middle one observed is an inactive path. Now both paths from A to D are going to be inactive. And since there are no active paths between A and D, it means that A is guaranteed to be independent of D given B and C. So the answer here is yes. All right, moving on. Is B independent of C given A and D? So here we have A and D shaded. And now we want to look at all paths between B and C. And we want to examine the triples along that path. So first we look at this top one. We see that it's a common cause with the middle one shaded, which makes it inactive. So the top path is inactive. Now we can look at the bottom one. This is a common effect with the middle one shaded, which is active, which means we found an active path from B to C, which means that B is not guaranteed to be independent of C given A and D. Okay? Next one, is B independent of C given A and E? Okay, so now we have, instead of D being shaded, we have a child of D. And if you recall from the D separation slide, if any child of D is shaded, that means the triple B, D, C is active. Okay? So here we have an active path from B to C through D. And so we are again not guaranteed that it's independent. Okay, so that's D separation. Hopefully that helped. Let's move on to queries. So the point of that last section was to be able to tell if two variables are independent of each other. The point of inference is to be able to answer a query that looks like this. Okay, so we want to be able to find the probability of some set of query variables given some set of evidence. And to do this, well, we're going to be working with kind of two basic operations. So we have a join operation, which you can think of as basically a database join. You start with two factors, one factor that depends on A and B, and a second factor that depends on B and C. And when you join it, you're basically just multiplying the two factors together while kind of matching up the matching rows in B. Okay? And you'll end up with a new factor that now depends on all the variables that you joined on, which for our case is just A, B, and C. So that's join. The second operation is eliminate, where you start with some factor and you eliminate a variable from that factor. So just starting with the F3 that we found above, if we wanted to eliminate the variable B from that factor, well, we would end up with a new factor that no longer depends on B because we eliminated it. And the way that we would eliminate it is we just sum out over all instantiations of B from that factor. Okay, so say we had an entry for plus B and entry for minus B. Well, we would sum those up, and then we would just have something that depends on A and C. Okay, so these are the two basic operations we're going to be working with. In class, we covered kind of two main algorithms to inference. The first was variable enumeration, and the second was variable elimination. Let's take a look at how these two work. Say we have a graph that looks like this, and we wanted to answer this query. So the probability of C, given that B is equal to 0. So B is observed, B is evidence, so here we have it shaded. For variable enumeration, well, we're going to have basically three steps. In the first step, we'll join over all of the variables, and so we're going to be combining all of the probability tables into one huge joint probability table. We're going to eliminate all of the hidden variables, and we do that by just, oh, by the way, a hidden variable refers basically to any variable that's not evidence or query. So any variable that doesn't appear in our query is a hidden variable. So step 2, we're going to eliminate all of the hidden variables. What that looks like is you're just going to be summing out over all of them. So for this one, in eliminating the hidden variables, we're just going to be summing over A and D from the factor that we found here, because A and D are both hidden, and then we're going to end up with a factor that now only depends on B and C. Okay? And then from this final factor that depends on B and C, or all of our non-hidden variables, all of our query and evidence variables, from there we're just going to normalize that distribution, and we're going to get the probability distribution that we want. Okay? So very straightforward, very easy to understand, but we're typically not going to be using the solution, and that's because to do variable enumeration, in the first step, you have to join over all of the tables, and you'll end up with some huge table here. Okay, so imagine that we have a much larger basenet with maybe 100 variables. Even if all 100 variables are binary, when we join over all the variables, we're going to have kind of this huge factor that has 2 to the 100 entries, which is infeasible. Okay, so variable enumeration is not the way we want to go because the factors that it creates are going to be far too big, right? So a better solution that we use is something called variable elimination, and it's very similar, except instead of joining over all of the factors in the beginning, what we're going to do is we're going to kind of join and then elim and then join and elim, so the size of our factors remains relatively small. Okay, so the algorithm is as follows. We're going to start with some set of factors, which is going to be initially set to just all of the conditional probability tables of the base net. And then we're going to loop through all of the hidden variables V. We're going to remove all factors with V from our factors set. We're going to create a new factor that's the join of all the factors containing V. And then we're going to eliminate V from that new factor. Okay, so this is going to create a new factor for us, which we then add back into our set of factors. And we'll continue until we've eliminated all of the hidden variables. After that, we'll just have a set of factors that no longer depends on the hidden variables, any hidden variables. We'll join up on all of those, and then we'll normalize the distribution to find our solution. I don't have an example for that in this slide because that would probably take too long, but there is a how-to video that Professor Abil did that you can find on edX, where he goes step by step through this process, and it can be very helpful. Okay, but let's move on to talking about sampling. So once again, we want to answer a question that looks like this. So the probability of some set of query variables given some set of evidence variables. And we've already learned a way to do this with Bayes net inference. So why do we need sampling? Well, basically it's because even for variable elimination, we can generate probability tables that are too big to fit in memory or too big to work with practically. So we want a way that we can kind of estimate this value, this probability value, without actually joining and eliminating probability tables. And sampling is going to let us do that. All right. So in class we covered a couple of algorithms for sampling. We have prior sampling, rejection sampling, likelihood weighting, and Gibb sampling. So this is basically a lot of material to cover, and it's pretty heavy material. So I'm going to try to go over examples of all of these, and hopefully that'll make it more clear. So let's get started with that. We'll start with prior sampling. So just talking about what it is. Prior sampling, as the name implies, is good for sampling priors, which just look like probability of A or probability of B, so nothing behind the conditioning bar. We can also use it to estimate conditionals, and that's what like the conditional probability table P of A given something looks like, but it's generally inefficient, and we'll see why. But the procedure is very simple. So to generate one sample, basically we're going to be going through all the variables in the Bayes net. We're going to have some linearized ordering of the variables. We're going to loop through the variables, and we're going to sample x sub I from the probability of x sub I given the parents of x sub I. Okay, and by nature of our linearization, when it comes time to sample variable x sub I, we will have already sampled all of the parents. Okay, so we'll have a full instantiation for the parents, and then we'll sample x sub I from that distribution. So it's very straightforward, but let's take a look at an example. Okay, so here I have the same probability table that we've been using, just this diamond shape with A, B, C, D. I've also included kind of all of the conditional probability tables, but those really aren't super important, so you can kind of just ignore those for now. I know it looks like a lot, but you don't have to worry about it for now. So let's just assume that we have this variable ordering, this linearization, A, B, C, D. Okay, so from there, let's create a sample using prior sampling. So we're just going to go down this variable ordering, starting from A. So we'll sample A first, and we sample A from the table P of A, and say we just end up with 0 for A. So we sampled 0 for A. Let's just move down the list. We'll now sample B. Now we sample B from the table probability of B given that A equals 0, right? Because we know what the value for A is above, so we sample from this table conditioned on A, okay? And say that we find that B is 1. Just moving down the line, we'll sample C from the probability of C given A equals 0, because once again, we've already sampled A. Now, when we're sampling C, we're going to condition on what we sampled for A, say that we get 0 for that. And then finally, we sample D from the probability table P of D, given what our sample value was for B and what our sample value was for C. Okay? And by the nature of our linearization, all of the variables that are going to appear behind the conditioning bar are going to have already been sampled by the time we get to D. Okay, so now all 4 of our variables are sampled, and we can just kind of return this sample A equals 0, B equals 1, C equals 0, and D equals 0. Okay? So if we continue this process a couple of times, we'll generate more samples. So say we generate these 3 samples. How do we go from this to estimating some probability table? We'll say we want to estimate the probability that A equals 0. Okay? The way to do this is very simple. Basically what we're going to do is we're going to go through and count the samples where A equals 0 and then divide by the total number of samples. Okay? So here in green are the samples where A equals 0. So the sample 1 is sample 3. So we have 2 samples where A equals 0 divided by the total number of samples. So we're going to estimate this probability to be 2/3. Alright, very simple. Okay, what if we were asked something that looks like this? The probability that A equals 0 given that C equals 1. Well, like I said before, prior sampling kind of isn't great for estimating conditionals, but you can still do it. So how do we answer this query? Well, since we have a conditioning on C equals 1, we can kind of only use the samples where we have C equals 1. So what that means is, since sample 1 and sample 2 have C equals 0, we're not allowed to use those samples when we're trying to estimate this probability. We're only allowed to use sample 3. So this is one sample where A equals 0 out of 1 total samples that we can use, which gives us a probability of 1. Okay? So you can still estimate this, but as you can see, we did kind of a lot of work generating sample 1 and 2, and all that work has gone to waste for this query. Okay, so prior sampling, not ideal for sampling conditionals. So how do we save on work if we know that we have some set of evidence? Well, one idea is to use rejection sampling. So rejection sampling is basically the same thing as prior sampling. You'll notice that the pseudocode is basically the same, except for this last line here. So what this says is, if x sub I is an evidence variable, and the value that we sampled for x sub I is not consistent with the evidence, then we're just going to stop sampling. And we're just going to return, and we're going to discard that sample. We're going to reject it, basically. Okay? So let's take a look at what that looks like. So once again, here, now we're trying to estimate this probability, the probability of A given that C equals 0. We'll start by generating our first sample. We'll work through the line. You know all this, so we'll sample A from probability of A, say we get 0. Sample B from probability of B given that A equals 0, say we get 1. And now we get C. Alright, so we'll sample C, like we did before, from P of C given that A equals 0. And say that we get 1 for the value of C. Now at this point, we basically know that we're not going to use this sample to answer this query here because it's not consistent with the evidence. At this point, we can stop. We don't need the value for B because we already know that this sample is never going to be used. So at this point, we'll just go ahead and reject this sample and move on to the next one without ever sampling D. Okay? Let's say that we end up with sample 2 and 3 that weren't rejected, and you'll notice that in both of these samples, C is consistent with the evidence because it has to be for rejection sampling. Now to answer a query, we're just going to do the same thing as we did before in prior sampling. So this is a better way to sample when we're conditioned on evidence, but you can still end up rejecting a lot of samples, which is still a lot of work that you're kind of wasting, right? So ideally, what we'd like to have is we just generate all these samples, and none of them get rejected, and none of the work that we do is wasted. Okay? So that's kind of the idea behind likelihood weighting. So again, likelihood weighting is also going to be used to calculate a query that looks like the probability of some variable given some set of evidence. But instead of kind of rejecting samples that are inconsistent with the evidence, we're going to force every sample to be consistent with the evidence. Okay? And then in order to do that, we're going to kind of assign each sample a weight, and that weight is going to be what we'll call the likelihood. Okay, so let's take a look at the procedure. Generate a sample. Initially, the weight for a single sample starts at 0, so every new sample will have a weight initialized to 1. We'll again go in some linearized ordering, and we'll say if x is an evidence variable, we'll fix x to be consistent with the evidence, and then we'll weight the sample by the probability that we would have gotten x naturally, right? So p of x given the parents of x. Otherwise, if x is not an evidence variable, we'll just sample it normally. Okay, so at the end of this, we'll have generated a sample and an associated weight to that sample. Okay, and that weight basically tells us kind of the likelihood that we would have generated the sample naturally. And with this weight, we then don't have to reject any samples, so none of our work goes to waste. Let's see this in action. Generating the first sample. Sample A, sample B. Now when we get to C, we'll notice that C is an evidence variable, right? It's behind the conditioning bar, so we'll fix C to be 0, and then we'll update the weight by the probability that C equals 0 given what we sampled before. So given that A equals 0, and we can just read that off of this table here, and we'll see that that's 0.6. And then we'll sample D like we did before. And so at the end, we'll end up with a sample which has A equals 0, B equals 1, C equals 0, D equals 1, and the weight will be 0.6. Okay? Very straightforward. Let's continue generating a couple more samples. So say we have 1, 2, and 3, and the weights are as follows, 0.6, 0.3, 0.3. Now, how do we use this to estimate this probability that we have here? So say we wanted to estimate the probability that A equals 1 given that C equals 0. We'll take the samples that are consistent with our query, so that are consistent with A equals 1, and we see that's sample 2 and sample 3. And then we'll take the sum of the weights of those samples divided by the total weight. Okay, so the sum of the weight of sample 2 and 3 is 0.6, and then the total weight of all 3 samples is 1.2. So we'll just divide those, and we'll end up with our estimation is equal to 1/2. Alright, so that's likelihood weighting. Our final sampling algorithm is called Gibb sampling. Gibb sampling is quite a bit different than the other ones. So for Gibb sampling, you're kind of only working with one running sample, and in every iteration to generate a new sample, you'll kind of tweak the sample that you already have a little bit, and that'll give you your new sample. So it's a little bit weird. But the procedure is as follows. So initially, we're going to randomly instantiate all our variables consistent with the evidence. So this is going to initialize our one running sample. And then in every iteration, we're going to choose some non-evidence variable x randomly. And we're going to resample x from the probability of x given all the other variables. Okay, so in every iteration, we only resample one variable, and that's going to give us our new sample. And then if we repeat this forever, we're guaranteed that we'll kind of converge to the correct distribution. So I don't have an example for Gibb sampling, but Professor Abil also has a great work-through video for Gibb sampling that I encourage you guys to check out. But that basically is going to wrap it up for this week on Bayes nets. See you next week.